Hey friends, it's Ben again. This is a video for Calc 3. It is on the notion of a change of variables. So what we're doing with change of variables is something you've already done a little bit. The specific examples that you looked at are doing a change of variables to polar coordinates and then doing a change of variables to spherical coordinates. One of the things that we'll accomplish today is actually the follow-up where we get the reason why dv turns out to be what it is in spherical coordinates. So that's kind of neat. Additionally, I guess this is the last video for the semester. So it's sad, it's bittersweet, it's melancholy, but you'll be happy to not have to look at my face anymore, right? Yeah, okay, whatever. So let's go ahead and take a look at what's going on with this and just see where it's going. So hopefully everything works right on this. Screen mirroring. Zoom. Yay. All right. So the topic is change of variables. So when we're changing variables, we have one coordinate system and we're needing to jump to a different coordinate system. So you're going to have some sort of equations going on with that that's going to relate your x's and your y's. So when we do this, we're going to have to think about not only the formulas, but also the geometry. Please understand that it's super hard to do this stuff by relying on only one of those. So the example that you might think about that you've seen already is x is r cosine theta and y is r sine theta. So soon we're going to have one where we let the x be u plus v and the y be u minus v, or something like that. All right. And when we do this, the x equals r cosine theta took a circle that's in xy coordinates, and then in r theta coordinates, it actually is a rectangle. If you think about this, our circle, maybe it's x squared plus y squared equals 1. Well, then that's going to have r equals 0 and r equals 1 on it. And it's going to have theta equals 0 and theta equals 2 pi. That means a circle is a circular rectangle. And that's a weird way to say it, but that's essentially the thing that's going on here. Okay. When we do some other setup for this, we will in general see that the new region is going to look somewhat like the old region. Not exactly the same, but somewhat. For example, what we will generally find is that if you have 4 sides and 4 corners, you're going to have 4 sides and 4 corners. We'll have an example where that gets weird and complicated, like really almost right out of the chute. But that is kind of your rule of thumb. You will just go through and say, here's my boundary here, and then you work out that it's the boundary, it's related to this boundary there, and then this one, and then this one, and this one, and this one, and this one, and that one. Okay, it's just you go through, figure out the boundaries, and figure that the thing that is contained within those boundaries must be the region that you need. Okay. All right. So for most of these examples, you're going to be given x equals something, y equals something. But sometimes it will be necessary to choose your transformation. If you're choosing a transformation, you have to carefully choose something in u's and v's so that you will simplify your integrand. For example, you might have something as simple as having, I don't know, the u be x squared, so that your function that you end up with is x equals square root of u. And it's just to eliminate some squares. So it's kind of a u substitution, but with multiple variables. Okay. Then there is this piece here. When you do your change of variables, you will end up then with this piece here that's referred to as a Jacobian. Okay, so take a close look at that. All I did, well, first of all, what I name it is partial of xy with respect to uv. And so this across the top is going to be the variables, that I'm starting with, and the one across the bottom is going to be the variables I end up with. So notice that across the top, I had partial x with respect to u, partial x with respect to v. So you always go through, here's your first variable, do that for the first row. Here's your second variable, do that for your second row. If there were 3 variables, you would put the third row to be the third variable, okay? And then our with respect to's, the first variable is u, so it goes in the first column. The second variable is v, and it goes in the second column. Simple progression like that, okay? So as you're going along here and you change an integral that's in x's and y's into r theta, uv, whatever it is, this little factor here is going to be your partial of xy with respect to, in this case, r theta, okay? So the setup for it is going to be relatively straightforward, but as usual, algebra will be messy, okay? All right, so let's see what happens here. And if you saw the octopus, the octopus in the slide here, and if that startled you, yeah, I'm with you. It's this particular example just happens to have a little bit of weird geometry to it, okay? But your setup is that we're given our transformation. We're given our transformation here. X has to be u squared minus v squared, and y has to be 2uv, okay? So we're going to use that in order to evaluate this integral here, the integral of the region of y times dA. Now, looking at the region, it's going to be bounded by y squared equals 4 minus 4x. If you solved for the x in that, you would get x equals 1/4 of 4 minus y squared, which suggests that you got something that opens to the left, okay? And then this y squared equals 4 plus 4x. If you solve for the x, you would end up with 1/4 of y squared minus 4. And so that means you have something that's going to be opening to the right, right? And I just put a rough sketch in there. You don't have to be super accurate with these graphs. But if you don't know what something looks like at all, whip out Desmos, do a quick graph there, copy it onto your paper. It's no big deal, okay? It doesn't have to be super detailed, all right? But then the other proviso here is we want our y to be greater than or equal to 0. So that means we draw the line y equals 0, and we want this stuff up here that's up above it, okay? I tried to color that in the best I could. My color in tool does not work with irregular pieces, so. All right, then what we're gonna have to do is to just go through and one piece at a time, figure out what the boundaries turn into. So for this one here, we're coming through and saying y is equal to 0. Well, y is 2uv, so 2uv has got to be 0. If you multiply 3 things together and get 0, one of them had to be 0. So either u is 0 or v is 0, one or the other, okay? And that's going to get a little funky here in a sec, right? Then for the y squared equals 4 minus 4x, we're just going to substitute in here and have the 2uv quantity squared equals 4 minus 4 quantity u squared minus v squared, which is a mess, right? But so in order to get something simpler out of this, what you'll do is to distribute out your 4's there, and then this 4u squared that you got, if you'll move that to the other side, then you can see that you have a factor of 4u squared that factors out. And here you get a factor of 4. Just cancel the 4's, all right? But now u squared times 1 plus v squared equals 1 plus v squared. So since we know 1 plus v squared can't be 0, if it was, v would have to be an imaginary number. And we don't mess with those in this class, all right? But since we know that that's not 0, we can divide it out. And so u squared is 1, so u is either plus 1 or minus 1. We don't really know which. Do the same sort of work for the other boundary, and you get v is either plus 1 or minus 1. Now is where the magic comes in. Because remember, we had that either u equals 0 or v equals 0. And now we got these 1's here that could be plus 1 or minus 1. Very technically speaking, we have this region, or this region, or this region, or this region. All 4 of those different regions would totally work for what we're doing, because they have all 4 of the same sides to them, right? And that's miserable. You want a direct answer. How do I do this? What's the one thing I do? And this, I'm starting you out with an example that has lots of little details in it, okay? But the thing that's going on there is that this u squared minus v squared and this uv that's in there means that you've got multiple representations. You've got a second order sort of polynomial going on in both of the transformation pieces. So that's why you end up having 4 of these regions, because it doubled twice with the second order, right? So we could use any of the 4 regions, but we are in particular going to use the one that has the u and v both being positive, because it's easier, okay? So that's what we're going to do for setting up this integral. All right, so now we're going to set up the integral. It is the double integral of y dA. So with our setup, we just turn the y into 2uv, and then we have to insert that determinant of the Jacobian matrix, and then we'll have to just set up our integral. So coming down here, we'll figure out that Jacobian. And so we, I didn't copy it over from the other page, but across the top here, we're doing the derivatives of x. Derivative, and x was u squared minus v squared. Derivative of that with respect to u is 2u. With respect to v is minus 2v. Then y was 2uv. Derivative of that with respect to u is 2v. With respect to v is 2u. Boom. You multiply the main diagonal. That's why we have 4u squared. And then subtract the product on the transverse diagonal, minus a negative, so we have plus 4v squared. Looks like a little bit of a mess, but fortunately, when we start integrating this, if we go, oh, I guess I went du dv instead of dv du, didn't I? So I guess that arrow I've got was absolutely the wrong arrow. I should instead have been drawing my arrow across in order to do the u's first. But, it's not too much of a deal here, because when you integrate with respect to u and you go 0 to 1, then you look and see what v values you're allowed to put in, and those go 0 to 1. Remember, the outside limit is always constants. This time the inside limit was constants too, so yeah. All right, so this seems like a little bit of a mess. Notice that factor of 2 and 4, so I'm going to factor an 8 out to the front, and I'll be left with inside u cubed v plus uv cubed. And I want to integrate that with respect to u. Now, you might be saying, hey dude, couldn't I go ahead and break that apart into integrals of just u and just v? A little bit, but not entirely, because this isn't something that you can factor nicely. The problem that you have, you can take a uv out of it, but then you end up with a u squared plus v squared, and that doesn't factor without complex numbers. So sorry. So we just integrate it, not a big deal. U cubed gives you 1/4 u to the 4th. U gives you 1/2 u squared. You're plugging in the zeros and ones, and I totally forgot to write that down here. So let me take care of that super quick here. Oh, super quick here. And then when you plug it in here on the next bit, the places where you plugged in a 1 will have just that 1 times the v, and the places that you plugged in a 0 will just vanish because, you know, it's 0. So once we've got to that, we might spot that we could factor out a 1/2. If you don't spot it, it's not a big deal, because in the next step, we just integrate. And so you end up with a 1/8 v squared and a 1/8 v to the 4th. We're plugging in the 1 and the 0 here. So you end up with an 8 times a 1/8 plus 1/8, which is a 4th. And a 4th of 8 is 2. So boom, boom, boom. So the integration in this wasn't hard. The setting up the integral wasn't hard. The transformation was hard, you know? So when you get something like this on the exam, expect it to be something maybe where straight lines turn into straight lines or something like that, because, you know, that makes this sort of thing a little bit easier to work out. So anyway, no big deal there. But that is like a full-blown example of what you do with these. So, all right, another quick example. So here we're asked to show that for this transformation, this weird, mysterious transformation you've never seen before, that the partial of xy with respect to r theta turns out to be r. You already know that from a geometric argument that was made before. However, now we've got it from the perspective of this change of variables, which is a little bit more general. Sometimes there's stuff that the geometry is just hard, and it turns out that the algebra gets it for us. So partial of xy, so the x stuff goes across the top, derivative of r cosine theta with respect to r, that's going to be cosine. With respect to theta, it's going to be minus r sine theta. Then the y's go across the bottom. Take the derivative of that with respect to of r sine theta with respect to r, you get the sine theta, and then r sine theta with respect to theta, and you get r cosine theta. Main diagonal gets you r cosine squared. Transverse diagonal gets you minus a negative r sine squared. Factor out your r, cosine squared plus sine squared is 1. Bang, that is why there is an r in your dA for polar coordinates. Pretty cool. Now, if you wanted to expand that to cylindrical coordinates, you would just put a z here and a z here, and then you'd have, you know, a 3x3 that you're dealing with, and you just have zeros and zeros and a 1 here, and you turn out to get the same thing. So in any case, that gets us the basic setup there. All right. So here we're going to let our r in this next example be a trapezoid with these vertices. Boom, boom, boom. Okay. And then the integral that we're going to look at there, can I make that larger? No, I can't on your screen. Sorry. Hope you can see it. It says e to the x plus y divided by x minus y. Okay. So if you've integrated some things with complicated crap up in the exponential, you know that those turn out to be a huge pain. So that's going to be rough, okay? But you're told to do the integration, and your region was something like that, okay? And you get to pick the transformation. Man, that is lucky. You got to pick the transformation. So you look in there and you say, e to the x plus y over x minus y. I'll pick my x or my u and my v to make that simpler. Now, in theory, you could pick u to be x plus y over x minus y. But then what are you going to pick v to be? Y? And If you pick it to be anything nice after doing that, it will not be a nice thing to work the rest of it out. So the most efficient thing to do on this is to just let the x plus y be u and the x minus y be v. Okay, you could have done the opposite and had, instead of u over v, had v over u. I picked it in this direction to illustrate something weird that happens. Okay, so bear with me on this. All right, so if you got u equals x plus y and v equals x minus y, if you add those two things together, the y's cancel, and then you can divide by 2 and find out that the x is 1/2 u plus v. If you subtract, then you find out that the y is 1/2 of u minus v. Okay, now if you're watching an online video other than my brilliant video, you may find somebody pulling a trick about inverse transformations, and the trick on that is totally workable, except if your transformation is something like example 1. If your transformation is not reversible, not something where you've only got 1 point to 1 point tied together. When those happen, then your inverse transformations might not exist somewhere. So just a caution, all right? I'm always trying to just do things the most straightforward way we can. And that's a trick that can be done, but I'm not going to try to talk about the trick. So, all right. Well, then for what we're working with here, we have got the derivatives going across there for the x's, and all we'll end up with is, man, I keep doing this. All we'll end up with is 1/2 and 1/2. And then across the bottom, we take the derivative of the y's, u and then v, and we get 1/2 and minus 1/2. So then when you go ahead and multiply the main diagonal, you get minus 1/4, minus multiply the transverse diagonal, and you get positive 1/4, but you're subtracting it. So we end up with a minus 1/2. Now, this hopefully will be a little bit frustrating to you because mysteriously I just dropped the negative. Poof, why do I do that? It has to do with the fact that you might have chosen u and v to be the opposite things. Okay, if you had chosen u to be x minus y and v to be x plus y, then we would have just reversed the two columns that we've got there. And if you reverse the two columns, you would have gotten a positive 1/2 instead of a negative 1/2. All right, keep that in mind for the next example. Because of that particular little nugget of information, always take the absolute value of what you get. If the thing that you get, having the absolute value of it's complicated, like it was absolute value of sine theta, well, don't do that. Just keep track of where it changes signs at. And that gets complicated. Super dissatisfying answer. Here's the right answer. The right answer is to just make sure you choose your u and v so that this never happens. However, every textbook that I can lay hands on doesn't give you that advice. It just says, it's a negative, just drop the negative. So I'm going to make a further comment about that in the next page or two. So, all right. So anyway, our integral that was e to the all that incredibly messy stuff now becomes e to the u over v times 1/2 du dv. And what we've got to figure out is how to transform our region. Okay. So this looks like a mess, I'm sure, but bear with me as we talk about it. So you've got that piece there is just y equals 0. So you substitute in what you've got for y and solve, and you can say u equals v or v equals u, however you want to put it. Then if we do x equals 0, we've got the same kind of thing, but we end up with u equals minus v or v equals minus u, however you prefer, right? Then if we've got this piece here, it's got a slope of 1, and it's got a y-intercept of -1, so it's y equals x minus 1. And if you were to get the x and the y on the same side, you would end up with x minus y equals 1, which is a nice and easy thing to substitute. That's just v equals 1, okay? Same thing for the other diagonal line. It'll turn into v equals 2, right? So if we're looking at what's happened here, then we've got this piece, this piece of this trapezoid turns into this piece of that trapezoid, okay? And this piece of the original trapezoid turns into this piece. There's something weird that happened there, and you may not have caught it. This piece turns into that piece, and this piece turns into that piece, okay? Here's the weird thing. If you think about going around this trapezoid counterclockwise, the places it was transformed to go around clockwise on the other one. It reverses orientation. That's what the negative is about, okay? That negative tells you that the two transformations reverse the orientation. There is an application in civil engineering that I am not qualified to talk to you about, where when you find out your transformation is negative, you immediately stop your manufacturing process or putting up your girders on your bridge or whatever, because it is going to turn your concrete pillar inside out or something, because that reversing orientation always breaks the materials, okay? So we have a negative flip there, and we just throw away the minus. Grr. All right, so now we're going to set up this integral here, and remember that it's e to the u over v, and then the 1/2, and I'm going to set it up du dv. Now, the advantage we've gotten here is that from the xy plane, if you looked at this, you could see it is not vertically simple, and it is not horizontally simple. You had to change as you went through. But here, we have something that's horizontally simple. So that's why we're integrating du first. So you draw your arrow going across, it enters the region at this diagonal line, which we said was, what is it, u equals minus v. And it exits at this other diagonal line, which we said was u equals positive v. And now we just have to say, how far does the v go? It goes down to +1 and up to +2. So our integral that we've got to actually do looks like it's kind of set up fairly nicely. The only really fearsome portion of it is that first integral, okay? So doing that first integral, you have to think about doing a u substitution, but since I already used the variable u for it, I can't really call it a u substitution. I'm going to do a double u substitution. Oh, I'm so punny. So if you do that, your dw is going to be 1 over v du, which means that your du, you would substitute in v times dw and go ahead and integrate. So I kind of did that stuff in my head here and just put in the factor of v that's going to crop up, and e to the u over v, and we're evaluating from u equals minus v to u equals plus v. So from that, we can factor out, we can factor out nothing. Haha, that'll show me. but we will come down here and we'll put in the u equals v, then u over v becomes 1. That's why it's e to the 1. And for the v equals negative, or u equals negative v, u over v becomes negative 1. And so now we've got v e to the 1 minus v e to the minus 1. Factor the v in there and just take and kick all this stuff that's constants out to the beginning. And now you just have to integrate v dv from 1 to 2. You can totally handle that, right? So we end up on this one getting 3/4 of e minus 1 over e. If you need a numeric approximation, whip out a calculator and do it. Doesn't really matter that much to me though, okay? I would advise on exams, don't bother with the calculator, just finish your exam a little bit faster. So, all right, last example here. So this time here, we've got a dv for spherical coordinates that is rho squared sine phi. And we want to go ahead and show why it is rho squared sine phi. Now, in the process, what we're going to run across is that the coordinate system that your textbook uses is stupid. It should reverse the theta and the phi, but it's written the way it's written. So, all right, so we know the conversion to spherical coordinates, and so we'll deal with the x's, and across the top is the derivatives of the x's, and we go just in order, rho theta phi, and so you end up with a sine phi cosine theta, a minus rho sine phi sine theta, and a rho cosine phi cosine theta. At this point, I'm going to sound like Charlie Brown's teacher. You are too young to know Charlie Brown. Man, okay. I'm going to sound like, I'm going to sound like I'm not making sense because it's just a bunch of symbols, right? You do the y stuff and you get this. You do the z stuff and you get this. It's kind of interesting that you get that 0 there, but z doesn't depend on theta. So it makes sense that we would get a 0 there. All right, then we have a 3x3 determinant, okay? And it might behoove you to try to watch a video talking more about evaluating determinants, but essentially we take the top row or any row and we expand across it. And so I take each thing in that row and make it the coefficient of something else, okay? And then what that thing is, I'll explain as we go here. So for cosine theta, we are going to then have a 2x2 determinant that we have to do. And the 2x2 is obtained by eliminating the row and column that the cosine phi was in. And so that means you transfer this piece down here, and now you've got a 2x2 determinant that you already know how to do, okay? For the 0, you eliminate its row and column, and you'll have these 4 entries to go in here. I didn't bother writing them down because I'm going to multiply them by 0. This is a strategy of evaluating determinants. If there's zeros, try to get them to be your coefficients to reduce your work. Now, there is a tricky bit here. You can see I have a positive for this, a positive for this, and a negative for this. It is another rule about determinants. You have a positive associated with the upper left, and you alternate signs for the rest of it in a checkerboard pattern. So since I am expanding across this bottom, I go plus, minus, plus, okay? If we'd done the vector stuff in Calc 3, like we should have, instead of pushing it off to Calc 4, cross products, you would have already learned this. So there we go. Anyway, though, so now we've got a big honking mess, except for this 0 part that we get to throw out. And let's go on and do the algebra, okay? So far, all I did here was to just copy the same things down. Then the next thing I said cosine phi times main diagonal minus transverse diagonal. Then I said minus rho sine phi times main diagonal minus transverse diagonal. The minus on the transverse, there are two negatives there, get a positive. Now, notice here also, we've got a negative sign to factor out. But once we factor that out, this feels to me like I skipped some stuff here. Okay, so this here, you can see there's a rho squared coming out of both pieces of it, and a sine coming out of both pieces, and a cosine coming out of both pieces. And if you pull those out, the thing that's left is sine squared plus cosine squared, which is 1. On this one here, you can see that you already had a rho sine phi, and you get another rho and a sine squared phi here, and another rho and sine squared phi here. And when you pull things out, you get a sine squared plus cosine squared, which, as we know, is 1. So that means this bit ends up with a minus rho squared sine phi cosine squared phi, and this bit has a minus rho squared sine cubed phi. So if we factor out the minus rho squared sine phi from both of those, we're left with a cosine squared phi and another plus sine squared phi, which is still 1. So that's the reason why we get minus rho squared sine phi. And then the fact that it's negative instead of positive means that we have stuff goofed up in the actual textbook stuff. I'm sorry. I'll tell you what, when I write my textbook, there won't be any mistakes in it. Yeah, it happens. All right. This video's run too long. I'm going to go ahead and let you all go. I'll see you in class. Somebody remind me in class to work out the formula for the area of an ellipse. Okay, that'd be a good thing to see in class. All right.